In this video, we're going to discuss the physical properties of alkanes, namely dealing with their boiling point, melting point kind of trends. And you see that I've already mentioned simple alkanes are gases. So we're talking about methane, ethane, propane, butane. All of these are gases at room temperature. And these gases make up what we call natural gas. Now, it happens that they are odorless. You might be saying, wait a second, when I smell gas, I smell something that smells kind of like rotten eggs. Well, the reason for that is because we put mercaptans, which are thiols, into the gas. Thiols smell like rotten eggs. And the reason for this is very simple. Since natural gas has no odor, you can't detect it using your nose, but you can detect very small quantities of thiols. And so it's very easy to figure out whether or not you have a gas leak or not. And that's why we use thiols and put them into our gas. Okay, now in terms of boiling point, the higher the molecular weight, the greater the boiling point. You can see this in your table in Jones, basically. But in essence, the more carbons you have, the greater the boiling point is going to be. Now, why is this? Well, in general, alkanes have very weak van der Waals forces. Remember, boiling point has to do with intermolecular interactions, right? So if two molecules have a strong interaction, then the energy that I need to add to break that intermolecular interaction is going to be greater, and the boiling point, therefore, thermal energy that I have to add is going to be higher. If I have very weak intermolecular forces, which in this case are only induced dipole interactions, then it doesn't take that much to break that intermolecular interaction. And so the thermal energy that I have to add is a lot lower. So alkanes in general have low boiling points. And as a matter of fact, this is why a lot of the small ones exist as gases, because at room temperature, there's enough thermal energy to break any of those intermolecular interactions. Now, as you extend the molecule, there is more possible induced dipoles throughout that molecule. And because of the increase in the number of induced dipoles, you therefore get greater attractions between two molecules. And again, the greater the attraction results in the higher the boiling point, right? So this is kind of a simple way of thinking about it, but it is certainly a way of explaining the difference in boiling points between pentane and neopentane. So pentane has a boiling point of 36 degrees. Neopentane has a boiling point of 9.5 degrees. What's the difference between the two? We see that they're both isomers. They have the same number of carbons in them. But if you think about the possibility for induced dipoles, neopentane is in a nice tight little ball. If you look at an electrostatic map of neopentane, there isn't the possibility of creating very many induced dipoles that can interact with another molecule. Whereas pentane is a longer chain and therefore has more potential to produce these induced dipoles. Hence, the interaction between two pentane molecules is a little bit stronger than the interaction between two neopentane molecules. And so we have to add more thermal energy to break that interaction up.